The Shroud of Turin has been hailed by some as the authentic burial cloth of Jesus Christ, while others have denounced it as a clever medieval fake. In an effort to determine the authenticity of the shroud, a group of scholars and researchers traveled to the Renaissance Cathedral of St. John the Baptist in Turin, Italy, to examine and study the shroud utilizing advanced scientific research techniques. Several of these experts participated in a symposium held at Elizabethtown College, Elizabethtown, Pennsylvania, where they presented their varying viewpoints on the issue of the shroud as an object of archaeological significance. The symposium was jointly sponsored by the Cultural Events Committee of Elizabethtown College and the Marguerite Ayer Wilbur Foundation of Santa Barbara, California. It was organized by Dr. W. Wesley McDonald, Assistant Professor of Political Science at Elizabethtown College. This program is the 7th in the series of 7 presentations on the shroud, videotaped at the Mystery of the Shroud of Turin Symposium, and features Walter C. McCrone, renowned microscopist and president of McCrone Research Institute, Incorporated, Chicago. He is the most renowned critic of the authenticity of the shroud.
I'm going to start out right with slides, but what I'm going to do is 4 slides about. I'm going to double project here today so that I can have more slides in less time, confuse you a little bit twice as fast. But I'm going to lead into it by relating it to the work that I've done in the past on art objects in general. And on the left is the Vinland Map. The Vinland Map, in fact, is how I got into the shroud in the first place. We did some work on the Vinland Map and found that the artist who produced it made a mistake. He was supposed to have done it in 1440, 15th century, but he used a 20th century pigment, titanium dioxide or titanium white. And usually forgers make a mistake. I give some lectures once in a while titled What Every Good Forger Should Know. And this involves picking the right materials of the right date. You couldn't paint a picture of Lord Nelson sailing into Trafalgar on a hovercraft. Somebody might know that that was not likely, if not impossible. And you can't paint it with pigments that post-date the time that the painting was supposed to have been done. So we look for incongruities in style and in painting materials, and then finally they have to have the same date as the materials that were used. White lead, for example, is white lead, but you can date it to different times that it was produced. So there are a lot of things that a forger has to worry about. We get many such things. This was one that attracted a fair amount of attention because it was regarded, hopefully by the Scandinavians, as proving that Eric the Red had gotten here before Columbus. The Italians weren't very happy about it. Fortunately, we were able to, in a sense, pull the rug out from under it by finding the wrong pigment. This is a map, not quite like the later one. It's supposed to have been done in the early or the late 18th century. And this was owned by my host at Bell Labs one day when I was giving a lecture there, and he was trying to kill time before my lecture and trying to make sure that I didn't get away. And he pointed out this map on his wall and said that it was very nice and very valuable and a very old map, and was there any way to authenticate it? And he had a microscope in his office. I said, well, if we can just get a little tweezer edges off of that, I might be able to tell something right now. I looked at it, and within about 30 seconds, I told him that it was done on paper that was laid mechanically, but in 1875. And my introduction that evening was a little bit cooler than it would otherwise have been. This is the basic way that is done. We have dates for the beginning use and for the end use of 50 or 60 at least of the pigments used by artists. This is just a selection of a few covering a reasonable range. It applies to other things besides paintings. This is a Mayan bowl, pottery, This came to us just a few months ago. An expedition in Central America had uncovered a real prize lot of hundreds of these beautiful bits of pottery, and unfortunately they brought them to us. I don't know why people bring anything to us. We don't find they're ever right. In any case, we used thermoluminescence on the pottery and found that it was 800 years old. That was just fine. Then if we'd stopped there, everything would have been all right and everybody would have been happy. But we checked the paintings, and again they had titanium white as one of the pigments, and that's a 1917 pigment. I sent them my report and my bill, and I haven't heard a thing from them since. I was asked by Ian Wilson after the Vinland Map was publicized as to whether the methods we used there might be useful on the Turin Shroud. And that was where I made my first mistake with respect to the Shroud. I said yes. And I proposed that we look at it principally with tapes. I wanted to see something from the actual surface of the Shroud, and I knew that we weren't going to be able to use razor blades and scalpels and scissors and so on to take samples, but I also knew that most people don't realize how much material you can remove from a surface with sticky tape. You lift fingerprints with them in forensic circles, and I've used them for years to collect dust samples wherever I've been, air pollution samples or just contamination in general. So I knew that those particles, any loose particles on the Shroud, and some not so loose, including many of the fibers from the threads themselves, should be removed by these sticky tapes. These are positions then of sampling. There are about 32 different tapes from both sides of the Shroud. They're a couple inches long, 5/8 of an inch wide, and probably, I haven't counted them precisely, but they're upwards of 30,000 individual linen fibers on those tapes, plus many, many particles of all kinds of extraneous materials, from mouse hairs to silk threads from the cardinal's robes, actually from the silk that wraps the Shroud most of the time, but many extraneous particles. And the problem was to relate the particles of interest to the subject of interest. The one on the right is a very low magnification picture of one of the tapes. That's the whole width of the tape, and we just made a record of all of the tapes that we had, all 32 of them. There's several hundred pictures like this, just indicating the appearance of the tapes as we got them. If you look at those with their top lighted there's no transmitted light, and the only light you see is reflected back from the fibers or any other particles that might be there. A few of those little particles are red, which indicated immediately that, I say red loosely, let's say it's an orange, reddish, brownish pink or something. It's the Shroud image color, let's say. But it did indicate that there is material, even on those tapes at that magnification, that might be related to the Shroud image. So we looked at some of them with higher magnification, and the one on the left indicates one fiber from a blood image area, and all you can see, what I'm going to try to do now is give you a short course in chemical microscopy along with this to indicate the interpretation of what we see here. These are two fibers, maybe 2.5 or 3.5. They've been worked on a little bit. They're a little bit broken up and frayed, one of them at least. They have dark spots. Well, the dark spots indicate, might say, dirty linen. And in a sense, that's the first thing to think of, that they're just dirt particles. They look black. The illumination is by transmitted light. And a microscopist thinks of two things when he sees particles like these on the Shroud, or on any subject, by transmitted light. They could be black particles, something like carbon black or air pollution, any black individual tiny particles, groups of them here. They could, however, a microscopist knows that they could be white. They could be red, blue, green, or any color you can think of. And this would happen if they happen to be very tiny in size, and if they happen to have very high refractive indices. And the reason for that being the requirement is that if they have high refractive indices, they bend light more. and the light that tries to come up through those particles to your eye just never makes it. It's reflected or refracted off to one side, and we call them pseudo-opaque. They look as if they're opaque black particles. And the answer to the question as to which they are is simply to use top light. This is the same view, same fibers, and with top light now instead of reflected light. They'll be dark where there isn't any optical discontinuity, and they'll be light wherever there's something that will hit the light that's coming down to the surface and bounce it back toward your eyes. So now we see, and well correlated with the black particles or dark particles over here, we see that they are reddish or orange or orangish particles. Fibers themselves, where the light actually was coming in from, my arrow's upside down here, the light was actually coming in from this direction and therefore is reflected off the sides of the fibers in that direction. But the particles are more or less round, so they're reflecting the light back no matter what orientation they're sitting. Then looked at them with a little bit higher magnification and looked at a number of different tapes and found that this is fairly general, that the linen fibers, this is an actual linen fiber here, this is a replica of a linen fiber. In fact, most of these are just replicas of the fibers. Once in a while where it replicates the fiber, it'll still pick off some of the image material, but here along the fibers themselves, the fiber itself is coated with not single particles. Well, they are coated with single particles, but at this magnification we wouldn't be able to see them. We can only see aggregates of, there are probably 10,000 particles along that length of fiber, and that's probably at least 1,000 particles there. And it's just a flat flake that, incidentally, since I'm at that point, probably is a loose flake on the surface of the shroud and was just picked off and, having meandered there, broken away from the surface of the shroud in the heavier coated areas. This one is a similar one. You might also be able to tell here that this is a replicated thread here. You can't see any of the thread, but you can see a suggestion that there's a lineup of reddish particles that were running in this direction, and were just, they stuck to the tape, the fibers stayed behind, and this just took a replica. It's called an extraction replica in microscopy, and we extraction replicate any kind of surface in exactly the same way. And you expect to be able to pick off particles and tell something about their composition and how they arrived there and their relationship to the substrate. This one over here is similar. It's a little higher magnification, and it was I put it in, and it's interesting to me because these particles have essentially the same color as all of these over here. This little patch, you won't be able to see it, but that one was a little bit rosier than the others. I found a few such patches where the colors weren't consistent throughout the whole shroud image fibers. I picked this one off and looked at it individually, and this is madder rose. I found very little madder rose. Maybe 3 times I found such places and picked them out and took a look at them. And to me, it's no more interesting than a few other crystals of orpiment and other artist pigments that I found on the shroud. Percentage-wise, it was parts per trillion or less. In other words, there were millions of times more of these reddish orange particles than there were the madder rose or orpiment. It's interesting, however, that to me that it indicated the likelihood that they were associated with, that the whole thing was associated with an artist in some way. The color is certainly different here than this, and that's of course what attracted my attention in the first place. This is another one. Obviously, again, this is replicating a surface of a thread running in this direction. Here's an actual thread and 2 more, or not thread, fiber. And this is just the material from the image area, and these are all blood. These were all selected from blood image areas just to make it easier to see them. You find exactly the same materials in body image areas as well as blood image areas. The only difference is in the amount of the two. That's almost true. The only thing that I said that wasn't quite true is that we find more vermilion, which I haven't talked about at all, as one of the red pigments. We find more of that in the blood image areas. And I'm not sure that that isn't essentially the only place where we would be able to find it. Turns out these are iron earth type pigments. Next slide over on the right is one of these at quite a bit higher magnification and with Hoffman modulation contrast to bring out the details a little bit better. At one point I thought that possibly the shroud was finger painted or the pigment had been applied dry. I no longer believe that for a number of reasons. One of them is that when I picked this one off and had it separate on a slide without any of the adhesive, these are still on the tape itself, I had difficulty picking these apart. In other words, it wasn't just a loose agglomerate of reddish powder, but it was glued together with something or other. And this is an organic binder that's holding this material together. And there are lots of voids in between them, which is mostly binder and just some of the individual tiny particles. And this is an aggregate of maybe a dozen or more. But there are a few hundred to 1,000 individual particles right in this portion of it. They're extremely tiny. Magnification up here on the screen is undoubtedly in excess of 10,000. The original picture was taken at 600, but that would be just 1.5 inches or so long. At that point, I was interested in several things. One, I was interested in the identity of these particles, and I was also interested in mechanism of application. And right away, I just mentioned the difficulty of separating this with 2 needles, holding it with 1 needle and picking at it with a second, and you had to tear it in half as the first step, and it was difficult to separate them. This portion right here is the top surface at a reasonable magnification, about 1000x on the original picture. This is an air bubble over here on between the glass surface and the tape. But these are the individual particles of the pigment embedded in a very thin film of an organic matrix of some sort, consistent with it being a paint medium. And very, very, very thin and very difficult to see. This does show vermilion, and this was from one of the blood areas, and there's no iron earth pigment here at all. Over here there is no vermilion at all. And the general, my general feeling now is that the shroud was painted at least twice, and maybe close to the same time, but with 2 different paints. One of them with the iron earth pigment, and then where they, in sense, needed a more intense image, used vermilion. The optical properties are quite different. You can see these are redder, and these are much more orange. And this is mercuric sulfide, or vermilion. This is an hydrated iron oxide. This goes up to higher magnification. Now, the original picture was at 1000x, and you can see a little bit better the individual particles of the iron earth pigment. The color of these pigments varies in 2 ways. Let's just forget this one for the moment and talk just about the iron earth pigments. These are very tiny. They average smaller than a micrometer in diameter. Their weight is of the order of 10 to the minus 12th grams, or picogram, which is pretty small. The color varies with composition because they're hydrated iron oxides, and the amount of water that's present gives you a lighter color. Some will be darker red than others. They might go all the way to anhydrous. They might even crystallize and become hematite. In that case, they have optical properties that are quite different from these, which are, in a sense, little gel particles, and with a lot of water still present. Again, the color varies with the composition. The percentage of iron determines the degree of redness of the individual particles. There's a complete range of them. Most of them are amorphous, non-crystalline. They're just little balls of gel. Along the way of dehydration, some of them crystallize, and you get things like limonite or goethite or lepidocrosite or finally hematite. And these are minerals that all iron oxide, hydrated iron oxide types, which are present along the way depending on the color and the degree of dehydration. there are many iron earth pigments. There are the siennas, raw and burnt sienna, and there are ochres, red and yellow ochre, besides hematite itself, and the umbers that have some manganese present. All of these are recognizable microscopically by color and by degree of crystallinity and by refractive index. This particular one turns out to be as close as you can come to a red ochre, and would be so classified. We could buy it from Winsor Newton today, and it would look very similar to this. The vermilion is an unusual form of vermilion, and looks well, yellower, obviously, or more orange, and was prepared by a method that I don't know. All I know is that I don't see that in very many paintings. I've seen it only in paintings that are dated before about 1600 AD. The modern vermilion is quite different. This shows the distribution of particles on a single fiber. This is 2500X over here, and this is from an image area, and it shows really the difficulty in finding these tiny little particles. It takes a powerful lot of looking before you can really be sure that you've got these real particles. In the blood image areas, you usually have larger amounts, and they're a lot easier and quicker to find. This is another one. This is interesting because it's one of two. The next one over here shows the same fiber. The difference is that this is focused on top of the fiber, the top surface. This is the bottom surface of the same fiber. So that portion is the same as this one, just out of focus. This that's out of focus is now in focus over here. And this I stress in a way because it means that the particles are dispersed individually on the surface of the fibers, individually, and around the complete circumference of the fibers. And this was completely general. Any time that I saw distribution of fiber or particles on tops of fibers, I could focus down and I could find another layer on the underside of the fiber. This to me says that the distribution both as individual particles and the distribution all the way around the circumference of the fiber tells me that it has to have been applied as a liquid. It has to have been applied as a paint of some kind, and a very dilute one and a very good one. When I tried to make a synthetic paint, I wasn't able to do nearly as good a job of dispersing individual particles as whoever did that. And I used ultrasonics, and I'm sure he didn't have that available. This is also high magnification, and it's also a top-bottom shot. So here we have iron earth pigments in focus on the tops. This is obviously out of focus, and this slide over here will momentarily show the same fiber, and now this is in focus up here. Everywhere I looked on any of the fibers, I could just focus up and down through and find particles on all surfaces, all around the sides and the bottoms. And no way I can see that existing or happening without it arriving in the form of a well-dispersed pigment in a liquid medium. This is the highest magnification shot I've got. It turned out to be very good in terms of showing the variation in individual particles. This is, up here on the screen, is close to 100,000x. The actual picture was taken at 2500x, and then is projected up a good 50 times beyond that. You can see here that some of them are pretty yellow, lighter in color, some are deeper in color. Part of it is due to the thickness of the particle. The thicker it is, the redder it gets. And the general idea might be that they're relatively uniform in color, but the thickness is not so uniform. But at the same time, sometimes you find pretty large particles that are pretty yellow, and you find some tiny ones that are pretty red. The pretty red ones that are tiny are hematite, and those are the ones that would be crystalline. They would show up between cross polars, for example, whereas almost none of these would. This would all be dark. The particles would all be dark. The fiber would be bright between cross polars. The biggest problem in all of this, and I think the problem that everybody has with me and the shroud and this sort of hypothesis, is trying to interpret these images. trying to see them in the first place. It takes a good microscope, very well set up, and it takes a microscopist well set up as well. It helps to have looked at such things before. This is the way blood looks on a cloth. At least it's the way my blood looks. I'll sacrifice anything for science. This one over here shows one of Pellicori's slides. I think he took this. Doesn't. I misspoke a bit ago. That last one, let's look at it, if you can go back to that. That's the one that's at the highest magnification. And I hadn't quite worked up to it and hadn't realized it. Again, you see the variation in colors, and they're bigger now, but they're still less than a micrometer across from this side to this side. Another very important point, too, here, and in most of the pictures you see of the pigment particles on the shroud, is that they have very dark borders. There's a very black edge on all of these particles when they're in focus. Everything here can't be in focus at one time, so some of them look like that one. But any of them that are in focus have very dark borders. And this is a reflection of the fact that they bend light, that light can't get up through them without being refracted at a very large angle. So the outer edges always look very black. And it means that the refractive index of this particle is very different from the matrix. Okay, the next slide then, coming back to the companion to this, is the blood on this side, and this is the shroud representation of blood. And this is very much a brownish image, and this is very much a reddish image. One other thing to note here that I think is important, this is a blood image area, and you'll notice that the tops of the threads are much lighter in color. I don't think they always were. I think that this is an indication that the shroud image was at one time quite a bit easier to see than it is today. Most of the blood pigment that's present still here, I didn't mean blood, I meant pigment that represents blood, of course. This is still present in the interstices and the cracks and crevices between the threads, but is, as you might expect, after 600 years, pretty well worn off the tops of the threads. I don't think it would have been all that difficult for an artist to have painted it at the time it was painted if he was painting something that was almost that uniform darkness in red all the way across here. This shows blood on a fiber. This is a taped fiber from the same cloth that you just looked at. So even though I may be anemic, this does not show anything like the particles that we see on the taped shroud. They're sort of a light brownish tan in color, and they don't have the dark enough edges to come anywhere near the type of pigment that we see on these shroud fibers. This now compares two fibers. Magnification here is about double what it is here. That doesn't matter. The appearance of these particles certainly is very different from this. This is real blood. This is shroud blood. This is a heavier deposition. This is a tape from the same actual blood, my blood on a piece of linen, and this just builds up, pick the thickest layer of it I could find to get a better chance of the actual color coming through. And this is not, again, anything like this. Let's see this slide. Similar particles. These are now at the same magnification, and there's just no resemblance between the two images. One is real blood, the other is shroud blood. At that point, actually earlier than that, having noticed that there seemed to be a lot more of this pigment in the image areas, and particularly in the blood image areas, I decided to make a blind survey of all of the tapes that I had, all 32 of them, to determine whether or not they had red pigments. In other words, if they looked like this, or even in some of the lighter image areas, I would just find a number of these, large number, but well dispersed and difficult to find. In fact, I goofed the first time through all of those slides by putting a couple of them over in this column. I didn't see the tiny pigment particles. But once I knew the answer, then I had no trouble finding the pigment, of course. when I went back through them and relocated those two, spent more time looking at them, there's another problem. The tape is about that long and about that wide, so it's more than a square inch in area. And some of the image areas that are extraction replicated are not that big. And I had cut the tapes in half at that point, so I had one half of each of the tapes, and the other half had gone back to Stirp. And some of the ones that I had probably are better in terms of finding pigment on them than the ones that Stirp now has, and vice versa. And in some of those that I went at too fast or didn't look carefully enough to see the ones that looked like this one. These are pigment particles, all those little guys. But finding them after you've done about 25 of them and you're getting tired of the whole thing anyway, it's easy to make that kind of mistake. But once tabulating them and going back to the two that were out of order and checking them very carefully, then I could, with clear conscience, put them all in columns like this and show that only those that were from image areas, taped image areas, had iron earth pigment, this should say, because it would be hydrated. And those that had no pigment were all from control areas, non-image areas. And then we have pigment that we can identify, that we can associate with image areas. The only time that we ever find any in control areas, and I just said there wasn't any, there isn't any of it that's dispersed as single particles on the fiber. There are some of the meandering, what I whimsically call blood clots in my notebook. I don't usually say it out loud anywhere. But the little particles of agglomerates that were loose on the surface and by folding and handling had moved around on the surface. There were a few of those. I've had half a dozen at least that I remember in the control areas, but they were pretty rare. This is a low magnification shot of a pigment that you can buy. It came out of the Forbes collection of standard pigments. And I compared all of maybe 75 different iron earth pigments from around the world that I had available, and any I could scrounge from New York University Institute of Fine Arts. And I looked at all of those and compared them with the Shroud pigment. And the one that I finally decided came closest, there were a lot of them that were very close. Most of them were Italian pigments, but most of the iron earth pigments in Europe came from Italy. This one is called Morelloni Buonamici, and it came from Florence. And this is low magnification. Over on the right will be a little bit higher magnification of the same pigment, and it doesn't look too different, I'm sure you would agree. But we'll go over here now to a higher magnification still, and you have the very dark borders. You have both the yellow and the orange and reds, and the size and the shapes are just the same. I don't say that it came from there because they all look very much alike anyway. I'm saying that it compares very, very closely. I would probably find it almost impossible with a light microscope to say that this was not the pigment that was used on the Shroud. If I wanted to really be sure, I would have to do trace elements in them or something of that sort to check it out. Let's see what's on the next side over here. Yep, that's even higher magnification. And we're up to about 5,000 on the original picture. But again, a good distribution of particles and very much the same size, shape, color, distribution of color and size and shape as on the Shroud. This is an example of taking this same pigment and making paint as close as I could make it to what I thought would have to have been used. And it was 10 parts per million of the Buonamici pigment in deionized water with 1% of gelatin as a medium. And I used this and painted it on the surface of linen, and then I taped it, and these are some of the fibers. This is the highest magnification that I could use practically under these conditions. And here we have some agglomerates. I said I didn't do as good a job of dispersing them as whoever painted the Shroud, but this is a little bit better distribution. This was a fainter image area. But again, they look very, very similar. This is, I thought you might be interested in seeing some of the charred fibers. they came in all degrees of yellowness, brownness to blackness. And of course, when they were pretty well burned or charred, they were pretty brittle. But these were present, in fact, on some of Max Fry's slides that we just looked at during the intermission a minute ago, or an hour ago, more or less. There were some of these particles clearly visible. This is just a yellowish fiber. This was another indication that there is a medium present on the shroud fibers, and it became pretty obvious based on looking at the samples and more or less one after another and noticing that there were more yellow fibers in some of the tapes than others, and then deciding that it looked as if more of the ones that had yellow fibers, like this one, also had pigment present. And I was lucky because that's a nasty job to give anybody to do, and I was tired, and I was lucky to find one of my students, Chris Curious, who was willing to sit down day after day after day and count and look at and tabulate about 8,000 individual fibers with respect to the percentage of yellow ones versus colorless ones in a given tape. And she had a number of these tapes. She had no idea which tapes they were, and came out with a tabulation then that showed maybe over here. If I look at my notes. Now this also bears on the subject of the medium. I think this is the discolored medium. Perhaps it gives cellulose some predilection toward decomposition, but at least the medium is acting like varnish on a painting or any of the media in which paint pigments are usually dispersed. And it yellows with age. Everybody knows that a painting has to be cleaned and re-varnished about every 50 years because the varnish gets so yellow that there are no blues. All the blues are now greens. And this is just a fact of life with paintings. And any medium, linseed oil to tempera, do the same thing. And I felt that this was a likely possibility that the medium which served, this was one of the image areas, body image areas. It does have a few individual pigment particles. They're tiny, and most of them are trapped in the nodes of the linen fiber. Over here is an indication that the same thing. I think that here, this is pretty high magnification. It was about 1,000 on the original picture. And this, I think, is a blob of gelatin or tempera, collagen tempera, on the surface of the fiber with the pigment particles embedded in it. This is all transmitted light, so we don't see any of the yellow or red or orange that we've seen before. But those are the same pigment, and it looks possible that this is a blob of the medium in which they're suspended and on the surface of the fiber. The reason we don't see it with darker edges is that refractive index is so close to the medium that there's no refraction occurring at that juncture. This is another one of the replicated surfaces of the fiber, which shows, I believe, a very thin film of this collagen tempera medium in which the pigment particles are embedded. The illumination system is quite different from the one over here. This is Hoffman modulation contrast. This is just ordinary transmitted light. But both of those, plus the yellow fibers, added up to presence of a paint medium. Now let's see what this says over here. This is another one. It's not the one I thought it was going to be, but it looks as if there's medium along here as well. Let's go to this one. This is the result of Chris's tabulation. I did a few until I got tired of it, but this it's laborious because whether you call it colored or not, normally would be decided whether you knew it was control or whether it was from an image area. But she didn't know that. So she was really, it sometimes took her 5 seconds or so to decide with an individual fiber which column to put it in. But this comes out very well in terms of correlating all control areas with the lowest percentages of colored fibers relative to uncolored and much higher amounts in the image areas. It added up to me to confirm very nicely that there was a paint medium. There was a reason for the shroud to be, the fibers to be discolored in that area. The presence of the pigment and the way it was dispersed indicated that it was a paint, and the paint medium has to turn yellow, so everything held together very well. At this point, I wanted to find out what type of medium it was, and I decided to use I used three different stains. These are histological stains that are commonly used for the purpose. This is the one most often used in the art world, and this is amido black. It doesn't look black, it's blue, but they call it looks black in the bottle. This is an agglomerate of what I believe to be the medium with dispersed pigment particles in it. Again, transmitted light, so with top light those are red, but here they're not. But this blue coloration here, and a general blue coloration on some of the fibers at least, and I think you can get a hint of bluish tint. And these incidentally had been washed with acetic acid, which is essential to eliminate just chemisorbed on cellulose type staining. And this was pretty common, well, it was completely common on all of the image area tapes that I looked at. This is another place wherever you find lots of pigment, as here, then the blue is more intense because presumably there's more medium there as well as pigment. This is another similar one. This sort of indicates the test works because this is an epithelial cell, skin cell. Should be same material. This is typical of gelatin, that it never disperses completely in a molecular state. Its molecular weight is a little bit high, and you get little colloidal particles. And I think this is one of the colloidal blobs of gelatin on the surface of the fiber, attached all around, completely around. Over on the right, this is one of the blood clots, in quotes, one of the meandering particles. It's an aggregate of, you can get some hint of red coming through here, but not very much. This is after it was stained with the amido black, and the medium itself is stained and the pigment particles still showing through a little bit. But it indicates that that's the same material as we have on the fibers. This is with fuchsin, which is a different stain for protein, and it helps a little bit in making it possible to see the pigment particles. It's not as dark as this. You can see the individual, even here, you can see individual pigment particles well dispersed. And again, wherever there is more pigment, there is more of the organic material that's stained with fuchsin. And that's a pretty typical fuchsin, or pretty typical protein stain. This is a place where it collected, and again, wherever you get some pigment indicated in most of these spots. I've just recently repeated a lot of the earlier work that I did just to reassure myself that I was on firm footing, and this was the first time that I'd used any of the other stains for protein, and they confirmed completely what I had found before with amido black. Another strange test, to say the least, is this one. At this point, I could only say that this is protein, which could be blood serum, or whatever, anything proteinaceous. Could be any of the temperas, could be cheese, egg, or collagen tempera. The only one of those, however, of those four protein types that doesn't contain sulfur linkages, doesn't contain cysteine, cysteine, or methionine amino acids, the only one is collagen tempera. So after checking for other media and knowing that this is proteinaceous now, then I decided I needed a test for collagen. And collagen would not do this. These are nitrogen bubbles, and this is a sodium azide solution, and for some reason unknown to me certainly, any particle that has sulfur linkages catalyzes the decomposition of sodium azide, and you get lots of nitrogen bubbles. We use it in forensic circles to test for fragments of hair or skin, any proteinaceous material that might be present, blood stains, blood serum, anything. If you have collagen tempera, this does not occur. This is a particle from the shroud, and these are pigment particles embedded in it. It was crushed down really thin. It was a very tiny particle, and that's between two glass surfaces now. You can see a yellowish color of the medium itself, And this is now in the same medium, sodium azide medium, and no bubbles. This indicates again that the medium itself contains no sulfur-containing amino acids, and therefore can't be cheese or egg tempera, and it cannot be blood. It has to be collagen tempera. It is proteinaceous, that we know. The only protein that I know of that doesn't have those 3 amino acids, sulfur-containing, is collagen tempera. And that would be expected because parchment is collagen, and scraps of parchment were used in the Middle Ages to make paints of this sort. This is a particle from the shroud, a couple fibers from the shroud. Looks pretty much the way it did before. This is in sodium azide solution and no bubbles. So again, there's no protein here that contains those sulfur-containing amino acids. There is protein there because this same fiber stained very nicely with fuchsin. These are 2 stains. This is made up with the same Buonamici pigment that I mentioned earlier. This is blood, and this is the pigment, the iron earth pigment painting. A couple points here. One is made up, this is the 10 parts per million of iron earth pigment in a 1% gelatin aqueous solution. I then put drops of that suspension of particles here. That was 5 drops, actually. This is 10, 15, 20, 25, 30, and so on, all the way around to here. And this is then obviously a graded series of spots. And because I knew what I had put into it, and I knew what volume I was putting here, and I was drying it between each application, then I know the amount of iron present in each one of these spots. The amount of iron is not very high, obvious. Probably the average on this shroud is somewhere along in this region. And it's around 2, 3, 4, 5 micrograms of iron per square centimeter. This is just about a square centimeter. It's about 12 millimeters across. I did the same thing with blood, and instead of spots you get rings. And the reason for this is simply that this is not dispersed particles. This is a clear solution. And it was diluted. It was a 3% blood in just deionized water. I filtered off some of the bacteria and a few other things, but otherwise it's just a clear solution. But the color is very different from the shroud. The ring formation means that it was a solution, and each drop that was put down traveled out to the edge of the drop where it evaporated and deposited the colored material, chromophore. Down here, the particles are not going to travel. They have some mass and some weight, and they settle out and they're trapped by the fibers, and the liquid itself moves out to the edge of the drop and evaporates, but there's nothing dissolved in it that's going to show up, at least. The gelatin is there, but it's still colorless at this early state. I just made it. So this is a good comparison of how an artist would have trouble if he tried to use anything like blood. Any solution, if he tried to use, he wouldn't be able to make a shroud image. But he would have no trouble making a shroud image with that kind of paint. This one, for the chemists that are present, I didn't detect the vermilion by light microscopy. And the reason I didn't is because the particles looked too much like the iron earth, and I just skipped over them and thought they were iron earth. But when we got to the electron microscopy, then I was told by, rather gleefully, by some of the electron microscopists in our lab that, how come you missed all the vermilion? Oh man, I mean boss. Knowing that it was there, I decided I had to be able to find it by light microscopy. So I went back and looked at it, and looked in blood image areas, and found that one blood clot, in quotes, that showed it, and showed the early, before 16th century type. And then I had to prove chemically, microchemically, that it was. This is the surface of a penny, and I'm using that as a reactant in a chemical reaction. The electromotive series, copper, this copper penny, copper is higher than mercury in the electromotive series and will displace from solution mercury ions and make little mirrors. So these are little mirrors of mercury on the surface of the copper that I made. These are all knowns that I'm playing with and before I sacrifice this blood clot from the shroud. And I did it by dissolving, first I had to dissolve the medium, I had to burn it away by a low temperature ashing with perchloric acid. And I did that in a tiny droplet. This is about 100 micrometers across, 1/10 of a millimeter. So I'm working with very tiny droplets. I put down the particles of vermilion in this case, known vermilion, and I put down a drop of perchloric acid, burn away the organic matter. That leaves the vermilion sitting there. I then put a drop of nitric acid on top, just the same size. I put in a crystal of potassium iodide. That makes hydriodic acid, HiO3, which dissolves the vermilion, and that's the only way I know of to dissolve vermilion. Immediately when it dissolves, the mercury in solution is displaced from solution by the copper. Copper goes into solution, and you end up with a mirror. So I made sure that I could do this down to sub-nanogram samples, and the amount that I used here, this was a Shroud mirror, not a very good one, but looked better when I looked at it through the scope. That was about a 10 picogram amount of mercuric sulfide, vermilion. So then I could say to them downstairs, well, if I had looked for it, I could have found it, even though I wasn't smart enough to look for it. They did some other work which held up very nicely, held my work up very nicely, fortunately. This is a fiber which I held back from them until I'd completed everything that I wanted to do, and until I'd written my 2 papers and published them. And then I graciously consented to let them have a fiber. And they took a look at this, and then over on the right side, over here is the same fiber taken with the X-rays of iron. And it's a way of mapping this particle for chemical content. Any element that you want to, you can detect here. And this is iron. So you can see that the iron pretty well fits spots on here where it looks like they're little blobs or something. This doesn't look like a clean linen fiber. I picked this one because it looked as if it had blobs on it. So this indicates that this is the medium plus the iron earth pigment. They then looked at some of the blood clots. I gave them about a dozen of these, and they're not very big. This is about maybe 8 or 10 micrometers across. Looks as if it might have particles in it. It's not a nice smooth polymer surface. And on the right over here will be again the iron map for it, and there's plenty of iron in it. So it's an aggregate or an agglomerate of iron earth pigment. They then went one step too far, as far as I was concerned, and did this whole spectrum of elemental compositions on another one of these particles. And here they found my iron. That's all right, that's here. But there's also, well, I knew this would be here, calcium and aluminum and silicon. Chlorine is from the tape. And these are what we call earthite. That's quartz and silicate minerals associated with iron earth pigments. But they found this. This is the mercuric sulfide, or vermilion. The mercury and the sulfur peaks fall on top of each other by this procedure. You can separate them out, and the next slide over here, maybe mine. Yeah, that's the particle, one of the blood clots, particle H it was. And this looks backwards, and it is, but it matches up with the next 3 pictures, which show the same particle with first iron X-rays. This is iron, and that's down in this corner. But this says there are a lot of high atomic number elements here. And they say, okay, let's look for mercury there. So let's look for mercury there on your side. Yep, that's mercury, and this one is sulfur. And that's right on top of that. The iron is down here and down here. So that was what first showed, the tracing was what showed the mercuric sulfide first. And then this showed that it was present in this one. This is painted on with in fact, this is from the shroud. And these are particles dispersed almost individually and in a liquid medium. You could not disperse them this way without a liquid medium. This is rubbed. And this is what I call snow fencing. And it's what you get whenever you rub with your fingers or with a dauber or whatever on a surface. And it can't help but clean off the tops of the fibers and pile up all the particles along the edges. And the appearance is so different from this that I can't conceive of this being the mechanism. I'm sorry to hit Joe with this, but since he's one of the few friends I have in the world, I shouldn't be so mean to him, but I do have to point out that he's right, it's pigment, but he's just putting it on the wrong way. Well, this is a picture done of the shroud by my favorite artist, Sanford. I had a hard job with Sanford. Sanford is a very good artist, and he can do the usual portraits of people. He's one of these guys that sits at art fairs and draws your picture for $5. His price is up a little now, but at least that's what he usually does. And I told him, Sanford, there isn't any light for this one. This is a shroud. You've got to pretend that it's in total darkness. And what would you do? What would you think this could possibly do to put an image on cloth? And we thought about it a while, and I led him along step by step, and we decided that the cloth might be touching in certain spots, so we'll put pigment where it touches, and that's the bridge of the nose and the brows and hair out here, anything of this sort, the chin and mustache. And after a while, this is about the 20th one, he finally got completely away from light and shadow and was doing something that to me was akin to cloth body distance. And this to me is about as close as anybody's going to get. He did this, was doing all these from memory. He'd looked at the shroud a number of times, and he did this one looking at the positive, or looking at the positive image of the shroud, but the actual photographic negative. So he was copying in a sense, but he had to make this reversal in terms of tonality. This is the negative, photographic negative of this. I don't think it's beautiful by any means, but it does look more lifelike than this one over on the right. And then just to leave you smiling, I hope not laughing out loud, I want to show you George Washington that I did. Now, you have to realize that I'm not exactly an artist. As an artist, I'd probably be a good dishwasher. But anyway, this was done looking at a picture of George Washington from an encyclopedia. And I tried to say, okay, the nose is bright because there's light hitting it, but it's not going to be that way on the shroud. So I'm going to take all the high spots and I'm going to make them dark, and I'm going to make something that looks like this. And this is not the negative of it over here, but let's see what the negative of it looks like. Fortunately, it isn't very bright, and maybe you can't see it very well. But I think that looks more like a rather sickly, sleepy George Washington than this one. I think that that's what happened. I think that the artist was commissioned to do a shroud. I think he did a fantastic job of it. He studied his lessons well and worked hard at it. He thought of a way to produce an image that would be reasonably acceptable as a shroud image, and he produced it. And I think by sheer accident on his part, it turned out to be photographic negative and to give a reasonable 3D figure when treated properly. That's probably the best place for me to stop. I would just say that the only colored materials that I found on the shroud and in image areas, and only in image areas, were inorganic pigments, plus the yellowing of the medium. I think if the pigment was not there, you wouldn't see the image. I don't think the yellowing of the fibers was enough to see. I'm sure that it had to be the pigment that was most visible. But I don't see any of the image materials, that is pigments, anywhere except in the image areas. And I can't come to any other conclusions than the ones that I've indicated. Thank you very much.
The Mystery of the Shroud of Turin, with Walter C. McCrone, is number 7 in the series of 7 presentations, videotaped at Elizabethtown College, Elizabethtown, Pennsylvania, where a panel of 8 scholars and researchers were brought together to present their views on the authenticity of the Shroud of Turin. The symposium was jointly sponsored by the Cultural Events Committee of Elizabethtown College and the Marguerite Eyre Wilbur Foundation of Santa Barbara, California. It was organized by Dr. W. Wesley McDonald, Assistant Professor of Political Science at Elizabethtown College. Information on the additional videotapes in the Mystery of the Shroud of Turin series may be obtained by writing to Action Video Productions, 1828 State Street, East Petersburg, Pennsylvania, 17520, or phone area code 717-560-0605. The Mystery of the Shroud of Turin programs were produced by Action Video Productions, East Petersburg, Pennsylvania.